So the last thing that we're going to cover in our sequences in series unit is finding a geometric series. Okay, so a geometric series, as you could probably guess based on what we did with the arithmetic series, it's just the sum of the terms in a geometric sequence. All right, and just like with an arithmetic sequence, we are saying that we are doing a finite sequence here. So we're looking at a point where it actually stops. Okay, now there's a lot of really interesting stuff when you look at sums of geometric sequences that are infinite. So, like if you had, if you added together 1 plus 1/2 plus 1/4 plus 1/8, and you just kept adding that for forever, what number would you add up to? So, it's pretty interesting stuff, but just for the sake of time for this year, we don't have enough time to go into it very in depth. So, that's something you'll probably hit in geometry. Okay, so we're going to look at the sum of an finite geometric sequence. Okay, so let's take a look at how this formula kind of lays out. All right, so for this one, I'm going to kind of walk you through a proof on how to do this. This is not something I'm going to ask you to recreate. I just want to kind of show it to you so you can sort of see how these things work. Okay, so what we are looking for here, all right, is we are looking for the sum of the first n terms in the sequence. So our notation for that is S sub n. So the sum of the first n terms. All right, and we know that a geometric sequence, the first term we just call a sub 1, right? The second term would be a sub 1 times r, right? The third term would be a sub 1 times r twice, right? And then a sub 1 times r 3 times, and so on until we get to the end of this sequence where we'd have a sub 1 times r to the n minus 1, right? To go from the first term to the last term, you multiply by r n minus 1 times. Okay, so that right there, that's our sequence that we want to find the sum of. All right, and to do this, we're going to kind of play a little bit of a trick here. Okay, so we're gonna do some math here, and we're gonna kind of go through this cool little thing. Okay, so what I'm going to do now is I'm going to take this entire sequence and I'm going to multiply it by negative r. Okay, so I'm going to take this whole thing and multiply it by negative r. So on this side, it'll be negative r times s sub n. You might be thinking, Miss King, why on earth are you doing that? You're going to see in a minute. It's something that is maybe not super inherent to like why you would do it until you see what happens because of it. Okay, so this is definitely something that like I didn't personally figure out how to do this. I kind of looked it up and was like, oh, that's a cool trick. Someone much smarter than me figured out that this would work. Okay, so what I'm going to do is, right, we're doing a giant distributive property. All of these I'm multiplying by negative r. So a sub 1, when I multiply by negative r, that's going to be negative a sub 1 times r. If I multiply a sub 1 times r times another r, right, that's going to be negative a1r squared. Okay, if I multiply this guy by negative r, it'll be negative a sub 1 r to the third. This times negative r, right? So you can kind of see all that's really happening is it's becoming negative and the exponents are going up by 1, right? So if we kind of followed this through and we get to the end, what's going to happen with this guy? Well, it's going to become a negative, right? And it'll be a sub 1 and r to the n minus 1 times r to the 1, right? You would add the exponents, so n minus 1 plus 1 would just work out to n. Okay, and if you need to stop and think about that for a minute to make sure that works for your brain, then by all means do so. Okay, so we've got these two equations, all right, and they're pretty similar. So what we're going to do now is I'm going to add these two equations together. That's the thing that you're allowed to do, right? That's how we solve systems, is we add two equations together because we know that if the first thing is true and the second thing is true, then the sum of them will be true, right? So I'm going to go ahead and add these equations together. So on this side, I'm going to get s sub n and then minus r times s sub n. So nothing really interesting happens over there. Here's where the interesting stuff happens, okay? Because as you kind of look at these two equations, you're going to notice something pretty cool, right? There's a positive a sub 1r here and a negative a sub 1r here, right? So if I add these two equations together, those are going to cancel each other out. Similarly, I've got a positive a sub 1 r squared and a negative a sub 1 r squared. That's going to cancel out, right? And then these guys, they're going to cancel out. And I didn't write it, but we know the next term here would be a sub 1 r to the fourth, right? So that would cancel with this guy. Okay, and again, I didn't write it, but I know that right before this one, there'd be a negative a sub 1 r to the n minus 1, right? That would cancel with that guy. Okay, so you kind of see now why we did this. We multiplied by negative r so that when we add these equations together, basically everything's going to cancel out. The only things that are going to be left over are the first term here, a sub 1, and the last term here, which is negative a sub 1 times r to the n. Okay, so we're getting there, right? This is a lot less complicated. But this is kind of annoying. If I want a rule to find just the sum, I don't want to have it looking like this. That's a little complicated. But you notice how the sum is a common factor in these two terms? So I'm going to go ahead and factor that out. So factoring out that s sub n is going to leave me with 1 minus r. And then if I want the whole thing, if I just want a rule for what s sub n is, I'll just divide both sides by 1 minus r. So my rule to find the sum of the first n terms of a sequence is you're going to do a sub 1 minus a sub 1 times r to the n over 1 minus r. And there we go. That's our rule. Now, one thing that some people do is you notice how in the top part here, there's a common factor of a sub 1, right? So some people will factor that out, right, and make it a sub 1 times 1 minus r to the n over 1 minus r and write it that way. Okay, so you'd also see it that way sometimes. It's the same rule. It's just a matter of whichever way you like it better. Personally, I kind of prefer this one, but either way is a perfectly valid rule. Okay, so that's our formula here. So this is what real mathematicians do, right? They find cool ways that you can prove things and find different shortcuts and formulas and things. So that's kind of what happens here. So our formula to find the sum of the first n terms, we just derived it. You take the first term, subtract the product of the first term and your rate n times, and it's over 1 minus r. Okay, so one thing to notice here, most of the time when we've been looking at formulas, it's always been r to the n minus 1, and that's not the case here. Okay, all right, or we said you could also write it like this. Either way is fine, they're the same thing. All right, so there's our formula. That's how you're going to find the sum of a finite geometric sequence. So let's take a look at a few examples. So this guy right here, we want to find the sum of the first 20 terms of this particular sequence. Pretty easy to see that our r is 3. We're multiplying by 3 each time. So I'd want to find s sub 20, sum of the first 20 terms. Okay, and I'm going to do a1, so 2 is my first term, minus 2 times the rate, which we said was 3, to the n, which is 20. That's how many terms we had. And then it's over 1 minus the rate. All right, now we got to put this in our calculator. So this top part, order of operations, kind of rules here. So we would be okay putting this whole thing in parentheses. If you're without parentheses. Okay, if you're ever not sure, better to be safe than sorry, add extra parentheses or do extra steps. Okay, so I'm going to get that number, great, and then I need to divide that by -2. Okay, if you can do that calculation in your head and just divide by the bottom number, awesome. If not, put it in parentheses. Oops, I didn't mean to type -3. There we go. Either way will work. So there we go. That's our sum. So the sum of the first 20 terms is this really long number, which should make sense, right? Because if you think about how big, right, the 20th term in this sequence, 3 to the 20th power times 2, that's going to be a huge number. So when you add them all together, it should be something pretty big. All right, so that's how we're going to use this guy. So this one down here, we're going to find the sum of the first 8 terms in this series. Okay, so looking at what's happening, my rate from here to here, that's -1/2, right? So my rate is I'm taking -1/2. So we'd say for this one, we're finding S sub 8, the sum of the first 8 terms. And the formula says you do the first term minus the first term times your rate raised to the n power. And then it's all over 1 minus your rate. Cool, so back to my calculator. Be really careful about your parentheses here. So it'd be 6 minus 6 times negative 1/2, oops, raised to the 8th power. I'm hitting all the wrong buttons. And then 1 minus negative 1/2 is going to be 1 plus 1/2. So divide that by 1.5. All right. Now, this is kind of a messy number. I want to have something nicer. These are all in fraction form, so I want my answer in fraction form. So I'm going to go to my math button, choose that top option to change it into a fraction, and there we go. Okay, so that is going to be my actual sum. Okay, so my sum for my first 8 terms is 255 over 64. All right, and that kind of makes sense, right? Because if I'm taking half each time, it makes sense that this bottom number would be a power of 2. All right, this guy, summation notation, works exactly the same way when you're talking about a geometric sequence as when you're talking about an arithmetic sequence, right? It tells you what term to start with, what term to end with, and what your rule is. Now, you might be looking at this and thinking, Miss King, that doesn't look like a right rule, right? Our rules were always the first number times the rate to the n minus 1 power, right? So what's going on with this guy, right? This 3 to the k bit, what's happening here is this is the same thing as 3 times 3 to the k minus 1. So it's k instead of r, no big deal, right? So your first term was 3 and your rate was 3. But you could simplify that expression to just 3 to the k. Okay, so that's all that's going on there. So from that, I can figure out what my first term is, and I can figure out what my rate is. But the beauty of a formula is that I don't need to do anything with this really. I just need this rule. So a sub 1 is going to be 3 to the first power, or 3. And then my 6th term, right, if I needed my 6th term, then, which we really don't here, but if I did, right, it would just be 3 to the 6th, and that's whatever that number happens to be. I don't need that here though, right? That's something you need for arithmetic ones, but we don't need that for geometric ones. Geometric's even easier. So for this one, to find the sum of the first 6 terms, that's what this tells me. Okay, then the rule is it's your first number minus the product of the first number times the rate to the n power, so we're going to the 6th power, over 1 minus your rate. Okay, so we did need to kind of look at it and interpret it this way to figure out what was going on here. All right, so then go ahead and calculate this. So 3 minus, I could do 3 times 3 to the 6th power, but if you have 6 threes multiplied together and then 1 more, that's the same as 3 to the 7th, right? And then I'm dividing that by negative 2. So 1092. And there we go. That's the sum of our first 6 terms. All right, and then this last one. This one is just a touch different, okay, because your initial term, we're not starting with the first term, right? We're starting with the 3rd term. So what I'm going to have to do to evaluate this, right, is I'm going to find the sum of the first 9 terms and then subtract from that the sum of the first 2 terms. Okay, you've done a few of these with arithmetic ones before. We've kind of touched on this, right? But the idea is that if you're adding together the first 9 numbers in a list and you don't want the first 2 because you just want to go from the 3rd to the 9th, then you just take away the sum of the first 2. Okay, so we're going to have to find 2 different things here and then we'll subtract them. So the sum of the first 9 terms, right, that would be my initial value minus initial value times your rate to the matching exponent, right? So the 9th power over 1 minus your rate. And then S2 would be starting number minus starting number times rate to the 2nd power over 1 minus 2. Okay, cool. We can figure this out pretty easily. So 5 minus 5 times 2, to the ninth, right? And we're dividing that by -1, so that's going to work out to positive 2555. I think I said too many fives there. All right, and then the other one is 5 minus 5 times 4, right? Divided by -1 would be 15. And then I just go ahead and subtract those numbers. So 2540. That is the sum. Sorry, wrote it backwards. Here we go. So that is the sum of the 3rd to the 9th terms. And again, the idea there is that we just looked at this and we said, okay, I'm going to find the sum of all 9 of them, and then I'll cut off the part that I don't want at the beginning. Okay, and that is the basics of geometric sequences, geometric series, arithmetic sequences, arithmetic series. And again, strictly when we're talking finite sequences. Okay, later on when you get to pre-calc, you will do a lot more with this, but this is just kind of a little bit of a foundation for you as you kind of go into that.